Hi, and welcome to Lecture 8 of the Deep Learning course. I'm Michael Cochet, and today we will be talking about learning with graphs. So this will basically be split in 4 or 5 parts. So the first part, there are 2 subparts. The first one talks about why we care about graphs and what graphs actually are. Second, part 1b cares about what embeddings are. Then in part 2, we will talk about the graph embedding techniques, basically combine these two aspects from the first part. Then we will talk about graph neural networks, which is a different way of getting graphs into neural networks. And then in part 4, we will talk about an application on query embedding. So now we have part 1a. We first talk about what graphs actually are and why we care about them. So in this context, I want you to think about when the last time was when you reconnected with a friend. Now, chances are that you have been using what is called a Facebook social graph. So what Facebook is keeping is a large graph with in their friends, people who know each other, what people do, and so on. Now, last time when you visited a doctor, now maybe not so much in Europe, but at least in other countries, like for example in the US, you would have tools like IBM Watson, which are very large systems, knowledge systems, which internally also keep a graph for representing certain key concepts and relationships within the domain. So a doctor can use that knowledge graph, you can use that system to, for example, search what the disease might be corresponding to certain symptoms. Now, another example is you might have been visiting a web shop. So you might have gone, for example, to Amazon, and Amazon is keeping a very large product graph. It means basically the relation between the different products they have. To give an example, they might give a relation between a washing machine, which you might have bought, and the washing liquid, which you actually need for it. Or you might have been doing a web search. That's maybe the most famous example. So Google is keeping a very large knowledge graph of all kinds of concepts. So that means, for example, painters, paintings which they have been painting. They keep cities, they keep the major of the cities, they keep the university where that major of the city has been studying, they keep other people in that university, and so on. So really these knowledge graphs or these graphs are all around us. Right? So there are a lot more examples. Some examples are about very general domains, like for the search engines and so on. Now we also find examples, things like, for example, Springer, which is mentioned here, or Elsevier. So they would keep knowledge graphs of research articles. So they can go from a very narrow domain to a very broad domain. Now, let's get back to basics on knowledge graphs or on graphs. So the simplest thing which we can do is what is called a simple graph. Right? So a simple graph, what does it mean? So we have nodes, also sometimes called vertices, and then we have edges or arcs connecting these together. Right? So that means that, for example, what this could represent is that these nodes here, these circles, they could be people, and the relation between them could be a friendship relation. So, and then this whole graph would basically be a friendship network. Now, what you can see in this graph is that we basically have sort of two parts. So there is this part of the graph, and then there is this separate part of the graph. And so we call this graph disconnected. It means we have two completely separate parts. A graph which is completely connected would be a connected graph. Now, one thing which cannot happen in a simple graph, but which we can add, is something called self loops. So in this case, we have the node here, and basically it has a connection to itself. So what could this graph now represent? Let's take another example. It could be that all of these nodes here, each of them is representing one atom, right? So this could be, for example, oxygen, which has a self loop because it can bind with itself. This could be other atoms which can then, because they have edges between them, which could bind to each other to form bigger molecules. Now, an additional thing which we can have on graphs is what is called multi-edges or multi-graphs. So it basically means between these two nodes, we don't have just one edge, but we have two. So now what could you do with this kind of graphs? Well, let's imagine we are now in this pandemic situation. So let's imagine that this graph represents which people have been meeting up with which other persons in the past month. So you have a person here, and this person, because there is this edge, we know that he has been meeting with that person over here. And now here there are two edges, so that basically means that two meetings have happened between these two people. So each of the edges basically represents one of the meetings. Another thing which we can do is we can give those edges a direction. So up till now, basically, we saw things like friendships or meeting each other, and these things don't have a direction. But now, in this case, we want to introduce a direction. So meaning that this direction has a certain meaning. So to give an example, let's imagine that this network is about Twitter, right? And it's basically about people following each other. So we have this person here, and then we have that person over there who is following that person. So basically that edge, the meaning of an edge and the direction of that edge means this person at the start of the edge is following the person at the end of the edge. So note that here, it is not in this example, but what could happen in principle is that people are following each other. So this person will be following that one, and this person then also follows that one. In that case, we would also need two edges to indicate. Another example, which also falls into this kind of graph, would be basically links between web pages, right? So if each of these nodes here represents a web page, then these edges could be links from, for example, this page to that page. Now, the next thing which we can do with graphs is give them labels, right? So labels and types. So what I've now done is basically on each of these edges and each of these nodes, I've just added a word. So for example, here I've said that this node is called Bob, this node is called double cream, this node is called cheese and so on. So what we can now say is that Bob actually likes cheese. So I also added labels on the edges, so they also get different meanings. Now we also have types. So it means that, for example, here we have a Bob, which is of type person, and all the other things here, so the double cream, the cheese, and milk, and so on, they are dairy products. So they are different. These nodes are of different types. Now I did one more thing in this graph, and that is basically I have here a directed edge, but I've mixed them with undirected edges. So I have both directed ones and undirected mixed together. Okay, so I made a small edit to the slide, so it's now even more clear what I meant by the types. So the yellow nodes would be of type dairy, and then the gray node would be of type person. Now, if we go one step further, we can create something which is called an RDF graph. And we still take a bit of a simplified view on them. So what basically happened is that instead of the labels as we had before, so it's simple textual labels, now each of these labels basically is a URL. So it's a unique identifier for these nodes. And this has real benefits when you try to, for example, merge graphs together, then they would have unique identifiers, and you can just merge unique identifiers together. Now notice another difference as well. So this graph has only directed edges. So we went from the one edge which we have here to the two edges for the similar to relation. And now I noticed I made a mistake. So this one should also be a double one. Moreover, I've added one special type of node here, and that is a node which has a literal value. So this is just a number in it, and in this case, it's the fat percentage of the double cream. So that is something which is possible in RDF. So, okay. Now, another thing which we can do in graphs is adding weights to edges. Right? So we have, in this case, we have basically just, again, gone back to the normal labels, and we have added these weights like 0.9, 0.8, and 0.5, and so on. So what this means depends on how you interpret now this graph. But in this case, it would mean that, for example, Bob likes double cream with a certain weight 0.8. He likes coffee cream with a weight of 0.9, so he likes it more as he likes double cream. Now these two things are similar, but only with a similarity score of 0.5, and here you have a similarity score of 0.8. Now, besides those weights, we can do a lot more, right? So we can also add other properties on edges. So here we sort of go all the way. So we basically say we have Bob. Now Bob likes coffee cream, but we add some more temporal or contextual information to it. So for example, here we say, well, he likes this coffee cream, but only in the evenings, right? And only together with coffee. So he doesn't just drink coffee cream, he drinks it only with coffee. Same here, so he liked double cream, but only with strawberries in the morning. So you can basically specify a lot more information on the edge, and these are then called qualifiers. So they basically give more information about the edge itself. So basically what we have now seen is that we could start from this simple graph and then go all the way up to this property graph, which we saw just before. And basically if somebody tells you like, okay, I'm using a graph for something, what you should immediately start, or what you should immediately start thinking is, or should start asking, is whether this is a simple graph, or whether it maybe also allows things like self loops, whether it's a multi-graph, is it a directed graph, an undirected graph, a mix of the two. Does it have labels for edges or nodes? Are they unique? Does it allow for properties on the edges, these qualifiers which we just saw? Does it have edge weights as a special case? And of course, combination of all of these things is possible. So the sky is sort of the limit with combinations here. Okay, so this was basically what I wanted to say about graphs. So next, we will be looking at embeddings.